brought you safely back in this program. I'm so glad to see people like George, like Martha. I'm very glad to see Benjamin back here again. Benjamin, for your information, Benjamin has been here since and he has never missed our lesson. And for that case, therefore, may I request Benjamin to open this session with an opening prayer. Benjamin, can you hear me? Hello, Benjamin. Hello, Benjamin. Benjamin, can you unmute? No, I cannot unmute. Joan, can you unmute, Joan?
Yes, sir.
Oh, good afternoon, Joan.
Good afternoon, sir.
How are you?
I'm fine, sir.
Oh, can you please open for us this session with a prayer so that we can begin?
Okay, sir. Let's humble ourselves for a word of prayer. Dear Lord in heaven, we thank you for the gift of life. Thank you for all that you've given unto us, the protection, the guidance. We thank you for this program. Dear Lord, as we are going to start our lesson, come and be with us, tabernacle with us. Send your Holy Spirit to come and guide us throughout the hour. In thy name I've prayed.
Amen. Thank you so much, Joan, for that wonderful prayer. I believe God has heard the prayer and God is going to be with us here. Once again, I welcome you to this session. For those who have just joined, this program is being sponsored by Edify Uganda. The brain behind this is ICC Teachers Association of Uganda, that is ITAO, who are making us study online, even amidst all other hardships. We thank Edify for providing for us these good services. We can't take it for granted. And we pray that God allow us master the concepts which we are going to be gathering from this session. I believe there are some people who are joining us for the first time. You have never heard of my voice. I'm called Teacher Alira Daniel. I love Senior 5 so much because when I'm dealing with A-level students, I'm dealing with mature minds. And guess what? They're always very active and they always behave in a mature way. So that's why I like A-level students. I teach physics and mathematics, but during this time, we shall be discussing physics. Those who have just joined, still, we are discussing physics paper 1, which I believe most of you like it most. I also like physics paper 1, it's very sweet. But sometimes I find physics 2 sweeter than physics 1. But the condition was when I go to the laboratory, then I find paper 3 as simple as, I don't know, maybe eating porridge. So I welcome you. That is briefly about me. I challenge you, I beseech you to make the best use of this platform. What we do here is thoroughly teaching. When you have not got a point, you have to feel free and you ask that question. I will be very free to you to re-explain everything. So don't feel shy, don't be ashamed that now I'm in the whole world. Why should I ask a question that I've not understood? No, we are in class. So when we are in class, you ask questions so that they can be answered. So make the best use of me, get the best out of me. Otherwise, I wish you the best in this lesson. Good. Let me start sharing on my screen. Maybe also to add on something little to the newcomers, in case there's something which you have not picked, you are all muted. So you raise up your hand. When you raise up your hand, I'll be in position to see that you have raised your hand. I'll ask you to unmute, then you ask your questions. Or in case of any submission, you can as well raise the hand, or you go in the chat section. This is the chat section. I believe you can see it. You go there and type, teacher, pardon on this. Teacher, what about this and this? We shall be in position to interact without any problem. I see Benjamin is having hands up. Benjamin.
Good morning, sir.
Good morning. How are you? It is already afternoon. How are you, Benjamin?
Hey, I'm fine. Okay. I'm sorry to say good morning, but it's afternoon. So I have a question.
Yes.
Last week we had looked about structure and mode of action of platinum resistance thermometer.
That is true.
But I never saw those notes in the Google Classroom, in our Google Classroom.
Oh,
I think
yeah, I think maybe you never search very well, but because I put it there together before we did the test, it was there. You go and search physics, okay? A level, you go under activity, okay? Under classwork. You go under classwork, you look for physics, you check very well. All the notes are there, okay?
Okay.
Okay, please. Fine. Thank you.
Thank you.
Joy Lovins, I'm happy to have you once again here. Thank you so much for being around. Good. We are going to start our lesson, that is thermocouple thermometer. We ended on platinum resistance thermometer, where we said platinum resistance thermometer works on the principle of Wheatstone bridge circuit. We also went ahead, we saw the mode of action, structure, advantages, disadvantages of platinum resistance thermometer. We also said when dealing with the platinum resistance thermometer, we don't use any other metal other than platinum because, first of all, platinum is this metal which has very high temperature coefficient of resistance. I remember defining temperature coefficient of resistance. We say temperature coefficient of resistance is the fractional increase in resistance per unit temperature rise. That one is in physics too. So we say we choose platinum resistant thermometer in preference to any other metal because platinum has very high temperature resistance, coefficient of resistance. Then two, the resistance of platinum varies linearly and continuously with the change in temperature. And so we use platinum resistance. We use platinum in platinum resistant thermometer, not any other metal. Today, we are going to see a gentleman who is called thermocouple thermometer. After thermocouple thermometer, we shall also see what we call to be constant volume gas thermometer. Good. With the thermocouple thermometer, please, I've told you already, my name is Daniel. Below is my contact. In case of anything, please feel free to contact me at any time at your free will. Good. Let's start with thermocouple thermometer. Please let me know by giving me a sign whether you can see on my screen well and my voice is clear. You can put a sign of okay, or you can type in the chat, yes, it's okay. Okay. Chat says, yeah. Good. Robert says, yeah. Benjamin says, yeah. Good. So let us start with construction of platinum resistance thermocouple thermometer. How do we make a thermocouple thermometer. I like physics. One, I like it because of two things. One, it is full of magic. Magic. When I talk of magic, you cannot believe me. But when I was in senior two, that was way back in 2008, when I was in senior two, the teacher came and was teaching pressure. He came and said that in pressure, in order for you to demonstrate atmospheric pressure, the existence of atmospheric pressure, who can tell us what you use in demonstrating atmospheric pressure? Which experiment do we use? How do you call that experiment? An experiment to demonstrate existence of atmospheric pressure. Who can tell us? Raise up the hand. An experiment to demonstrate the presence of atmospheric pressure. Hello? You can raise up the hand. You can give me in the chat. Let me check. Good. John says can method. Please, John, elaborate more. Which can are you talking about? Please, John. Crushing can. Very good. Drusla says crushing can. Very good. I want only that. Crushing can experiment. Washongoma. Wesonga. Uh-huh.
I was saying the same thing. Crushing can.
Crushing can. Very good. It is a crushing can experiment. Now, the teacher told us that when you get, let's say, a jerry can, when you get a jerry can may not be heated. Like let's say you get a tin. When you get a metallic tin, you put water in the tin, then you boil that water. You boil. Then after boiling and the steam is coming out, you cover it. After covering, you stop cooking, you're boiling it. Then you pour water. You pour water immediately onto that can. Let me tell you, the teacher said the can crashes. I used to say, but teacher, no. How is that possible for sure? Just pouring water and it crashes? Let me tell you, I took an initiative to do it practically and I found that it was true. That is when I came to conclude that physics is magical. It is magical. Now, you hear another magic here. Let's see another magic here. When I get a metal, do you hear me? When I get a metal, let's say copper, okay? And then I get another metal, let's say iron. Do you hear me? I get a metal, say copper. I get another metal, say iron. I join them together like this. Then I put this one in a hot place. Hot place. If I put this one in a hot place, I put this end in a cold place. Cold place. Did you know that the current will be produced? Oh, did you know that the current is going to be produced? If I connect a milliammeter here, the milliammeter will be deflected. Did you know that? That is the magic which we have in physics. When you get two different metals, let's say metal 1 and metal 2, then you join these two metals such that they have two junctions. There's junction 1 and junction 2. So if these two are joined as junction 1 and junction 2, and you keep one junction in a hot place and another junction in a cold place. Physics has found it out that current is going to be produced, which produces an EMF. So an EMF is going to be produced, and that EMF is the electromotive force. That effect in physics, we call it to be thermoelectric. We call it to be thermoelectric, that effect. And the whole arrangement is called to be thermocouple. So if I'm to ask you briefly, can you explain how a thermocouple can be produced? Bosco says, teacher, are we doing it practically so that we can also see? Oh my God. Yeah, probably we don't have the laboratory, but if we had, we would do it practically so that you can also see these things work. From water to produce current. No. Benjamin says, from water to produce current. No. Benjamin, it is true. If I put this one in hot water, I put this one in cold water, current will be produced, and EMF will be what? Will be produced. Good. So, can somebody briefly from this explain to us how a thermocouple is constructed? You can raise up your hand. Raise up the hand. How is a thermocouple constructed? How is it made from my explanation? What you have got? You can raise up the hand. Yes, John says, John is answering Benjamin. John is saying yes, because the wires are different and hence creating EMF. Very good, John. John, you answered it very well. I'm waiting for somebody to raise up the hand to explain to us briefly now. Patricia? You can talk, Patricia. Okay, let me see Andrew. Andrew?
Yes, good afternoon, sir.
Good afternoon, how are you?
I'm fine. I would say that two different wires made of different materials are connected at both ends to make two junctions.
Good.
One junction is placed in hot water, another junction is placed in cold water.
Yes.
This results into production of a current.
Yes.
That's what I would say.
Very good. Thank you. John says, teacher, what is Seebeck effect? Very good. Seebeck effect is thermocouple effect. I mean, thermoelectric effect. That is Seebeck effect. Seebeck effect is the phenomenon or is the effect which results into the production of an EMF when two dissimilar materials or dissimilar objects are joined together with two junctions kept at different temperatures. Let me have answered you, John. The Seebeck effect is what we have been looking at here. Two dissimilar materials connected at two junctions, joined at two junctions, and those two junctions are kept at different temperatures, resulting into production of an EMF. Is that okay, Joan? You can let me know in the chat. Okay, she says, thank you, sir. She says, thank you, sir. Good. That is Seebeck effect. So, in the constructions of an EMF, we are saying two wires. We have already talked about this, so allow me go a little bit faster on it. Two wires of different materials are joined together to form two junctions. So this wire may be copper wire and iron, copper wire, aluminum, aluminum, iron, whatever the case may be, as long as they are different wires. So you join them to form a junction, two junctions. Now the two junctions are then maintained at different temperatures. So those two junctions are maintained at different temperatures. Then a small EMF is created. It is small. A small EMF will be created, and this effect, I already told you, the effect is called thermoelectric or Seebeck effect. And the arrangement itself is called a thermocouple. So that is briefly the construction of a thermocouple thermometer. Good. Let's see its structure. How does it look like? This is a thermocouple thermometer. This is the line drawings. It has copper wire joined together with iron wire. They are meeting at this point and at that point. So this milliammeter has to deflect as long as these two ends are at different temperatures. So this is the structure of a thermocouple. Good. Let's move on. I said, in case of any question, anything, you can let me know so that I can re-explain. I want us to be experts in physics. How does it work? Joy Lovin says, I'm wondering whether you defined it. Oh, Joy Lovins, raise up your hand, Joy Lovins. Joy Lovins, can you raise up the hand? Joy Lovins. Oh, good. Joy Lovins, can you define for us a thermocouple? Joy Lovins. Hello, Joy Lovins. Sorry, we can't hear you well.
I'm like, I don't know the difference.
Hey, it's a thermometer. Really, we cannot say define a liquid glass thermometer or what is platinum resistant thermometer. What we can do about it is that we can describe it. We can describe it. Good. John says, sir, please explain about its disadvantage. Yes, we are going to come to the disadvantages along the way. Let's see how it works. Your lovelies, this is a thermometer. We can explain the structure, the mode of action, but really if you say that we define a thermometer, a platinum resistant thermometer. A thermometer is a device that measures the temperature. But if I say, what is a liquid glass thermometer? Maybe I tell you that is a type of thermometer that uses what? Liquid. Okay. Fine. Let's see how it works. Now, when it comes to mode of action, it's very simple. One, we first get the EMF at steam point. After getting the EMF at steam point, we get the EMF at unknown temperature. After that, we get the EMF at 0 degrees Celsius, just like how we have been using these other thermometers. So, in our mode of action, we shall say the hot junction. The hot junction is placed in a body whose temperature, theta, is required. After placing it there, you measure the resulting EMF and then you call it E what? E theta. Then this very junction is then inserted in an ice-water mixture. When you talk of ice-water mixture, this is 0 degrees what? Celsius. So it is then inserted in an ice-water mixture, and the EMF E naught is noted. Then from there, we put it in an enclosure of steam. We then insert it in a steam which is coming from pure boiling water at standard atmospheric pressure. This one will be at 100 degrees Celsius. Then we record it as E100. Then from there, we calculate theta as normal, the way we have been calculating. We calculate theta from E theta minus E100, E naught over E100 minus E naught times 100 degrees. There, you will have successfully calculated temperature using thermocouple. So what you do, you put the hot junction in steam, you measure the EMF E100. Put the hot junction in ice, you measure the EMF E naught. Put the hot junction in a temperature, in an enclosure whose temperature is required, you call it to be E theta. Then from there, you calculate theta from E theta minus E naught over E100 minus E naught times 100 degrees Celsius. Is that okay, friends? Is that fine? Oh, they say yes, yes. You can let me know. Other people, in case of anything, you can let me know still. Now, that is how it works. Benjamin says yes. Andrew says, pardon. I cannot state that. I will pardon right away. If you want to use thermocouple thermometer, what you do, you get the hot junction, you put in steam. You measure and record the EMF as E100. Get the hot junction, put in ice, measure the EMF as E0. Then you put it in the body, which you want to determine the temperature. Then you measure the EMF as E theta. Then you use this formula to get the temperature. Is that okay? My brother Andrew, are you okay now, Andrew? You can let me know in the chat. Andrew? So it's okay. So, yes. Stephen Jubek says, so is it okay to begin with measuring the E100 first and then follow the other steps? Yes. The order does not matter. Whatever you want to start with, you can start with it. You can start with E theta, E100, E naught. You can start with the E100, E theta, E naught, whatever the case may be. I see Op is having hands up. Please go on and you ask your question, Op. Or the submission.
Thank you for the service. So I'm just inquiring if you're using the hot junction to measure the other temperature, what happens to the second junction?
The second junction is kept in that very cold junction, okay? By the way, we can either use hot junction or cold junction. Is that okay? Yeah. You keep this one here. Let me draw this. Let me hope you can see on my screen. You keep this one here. Then I transfer this. I put in in steam. Then I record. Then I transfer it. I put in ice. I record. I transfer it. I put in water. I mean, in the temperature in the body whose temperature is recorded, is needed. So as long as the temperature between this and this is there, or they don't have the same temperature, you'll measure the AML. If the temperature of this point is different from this, you'll measure the AML. If the temperature of this is not the same as this, you still measure the EML. So the EMFs will be there as long as there's temperature difference between these two junctions. Likewise, you can use the cold junction. You keep this one in the warm one. You pick the cold junction, put in steam, put in ice, put in the temperature in the body whose temperature is required. Still, you get the results. Is that okay? That question was asked by, hope you can let me know in the chat if it's fine now so that I move on. Okay, good. Let's see advantages, and this Faith Nora says, okay, Op says, okay, good, Op. That's great. Let's see some of the disadvantages and some of the advantages of this gentleman whom we are calling to be optical parameter, I mean, thermocouple. When I was still studying, I used to the only point I would not forget was this one. This first point I would forget others, but this one no, because this is the only thermometer that measures the temperature at a point. We have been discussing thermometers. Did you find any thermometer which could measure the temperature at a point? Can you let me know? Did we find any thermometer which can measure the temperature at a point? And was there any thermometer you could measure the temperature at a point?
No.
No. This is the only one that can measure the temperature at a point. By the way, why? It is because of this sharp part. You see this sharp part? This sharp part, you can put it in the nose, you can put it in the ears, you can put it anywhere. It can measure the temperature of a point, hidden place. It can measure it. It can measure that temperature because it can enter anywhere. As long as it is able to enter and it reaches there, then it can measure that temperature. So, one of the advantages of this thermocouple is that it can measure the temperature at a point. Then, I like the second point. Rapidly changing temperature. Now, be careful. This one can measure rapidly changing temperature, but it cannot measure a temperature which is changing slowly. It cannot measure it. This temperature which is changing rapidly and not slowly. Yes, Wesonga, can you unmute?
Okay, teacher.
Yes, Wesonga.
Teacher, okay, I'm getting the point.
Yes.
About how the EMF is created and how the temperature is measured. But my question is that the cold junction has to be in ice or just normal cold water? Like, does it matter where it is?
The cold junction.
Yes.
Oh, the cold junction you can choose the temperature. You know, you can choose the temperature. You can say, let me keep it at 10 degrees Celsius or at 0 degrees Celsius. You don't want to choose, but as long as there is a temperature difference between the first junction and the second junction, then automatically an EMF will be generated. Is that okay, Weshonga?
Yes, teacher, and also
Yes.
Which means the cold junction can be in a liquid and the hot junction can be on a body. It doesn't matter.
Yes, as long as there is a temperature difference.
Okay,
is that okay?
Yeah, thank you.
Okay, please. Can we move on?
Yeah.
Okay, let me mute you and then we go on. Good. So it can also measure rapidly changing temperature. Nothing we can talk about that. Nothing we're going to say much about that. And while measuring rapidly changing temperature has high thermal conductivity, we're going to see this ahead, and small heat capacity. I like this. Members, let us see this point. Is there any thermometer where we do not say that this is its advantage? Please, I'm giving only 1 second. Is there any thermometer which does not measure a wide range of temperature? Because this point has been repeating itself from the beginning up to now. Is there any thermometer which does not measure wide temperature? Please let me know. And if you say yes, you tell me the thermometer, raise up the hand. I want to see those who have been following very well. Somebody tells me in the chat, no. Joy Lovins, be careful. Joy Lovins, be careful. I see Benjamin. He's having hands up. Benjamin?
Yes, there is.
Which one?
A mature glass thermometer.
Very good, Joy Lovins. Benjamin, very good, very good, very good. It is only one, and that one is the liquid in a glass thermometer. It is the only thermometer which cannot measure a wide range of temperature. The rest will always measure wide range of temperature. Wesonga says, what about liquid in a glass thermometer? Wesonga, very good. It is that one. I was testing us. Good. So other thermometers, all other thermometers except liquid in a glass thermometers have wide range of temperature. Good. It can be used to determine direct reading if connected to the galvanometer. Then lastly, you can steal it from the laboratory, by the way. It is portable. One day I was in class, then I told somebody that it is portable. Then the person said, are you sure, teacher? You can, it is pocketable. Huh? I think portable is pocketable. Is that true? Yeah. So it is portable. You can take it away from the laboratory and take it wherever you want it to be. This is the, we have been talking about it, but it's here. I see a chart. Benjamin. Benjamin is saying that, teacher, why should we steal it? Yet I can make it. Oh, that's good. You can make it, but still to increase the number probably, so that you can have many stocks. Oh my God. So this is platinum resistant. I mean, this is thermocouple. Do you see the thermocouple? Let me hope you can see it. This is one junction. You fix one junction, then you start putting now this one. You put in ice, you put in steam, you put in the body. So you fix this junction. When you fix this junction, you put this one in ice, put in steam, put in that. So you can carry this wherever you want it to be. This is only one type. There are very many types, of course. There are very many types. I've picked only one of the very many types. We can make it locally together in the lab. So this is already a manufactured one. Disadvantages. I told you one of the disadvantages already, that it cannot measure temperature, which is changing slowly, please. It only measures temperature which are rapidly changing. Mukama, it is it is very inaccurate. Allow me explain this. Very inaccurate in a sense that, you see, it is made up of two different materials. So being made up of two different materials, which are metals. Now, these are metals. These metals have resistance. All conductors have what? Have resistance. Even the battery, which we use to produce electricity, has resistance, called the internal resistance. The connecting wires have resistance. So, when current is produced, as it flows, it is being consumed by the what? By this resistance. Because for an EMF to be produced, then that means that there is current which is what? Which is flowing. So the current which is flowing is some of it is consumed by what? By resistance. So if it is 12 amps which has been produced here, what reaches here is not 12 amps, but you'll find that it is 11.2 what? 11.2 amps. Where has the other 0.2, 0.8 gone? It will have been consumed by resistance. And so what we read directly here is not actually what is produced. It is what is produced, but less by what has been consumed by the resistance. Is that clear, members? So that makes it not to be accurate enough. Is that clear, members? Okay, good. Yes, 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 yes. People are saying yes, 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 yeah. Good, Wesonga. Good. So that makes it not to be very accurate. Then this is just an NB. EMF can be generated from a junction if, one, the junctions are made from different materials, then two, the junctions are at different temperatures. That is when the EMF can be generated. We have successfully seen a thermocouple thermometer. So when we are talking about thermocouple thermometer, one thing which you need to note is that you need to know the construction of a thermocouple thermometer. You need to know how it works. You need to know the advantages. You need to know the disadvantages. So those are the four main things which you need to know about thermocouple thermometer. Good. Let's go to yet another gentleman, that is constant volume gas thermometer. I like this thermometer. I like this thermometer. And I think because other people also like it. Because when I look at this thermometer, it reminds me of senior 2 work pressure. Good. I'm going to ask a simple question. I believe if we are all real physicists, then we are not seeing this for the first time. This one is a thermometer here, but it is used to be called some other thing in physics 2, senior 2. Who can remember the name of that thing? Raise up the hand. You can raise up the hand. How is this? How was it called in this senior 2 physics? You can raise up the hand. How was it called? Oh, don't tell me that you don't know. Don't tell me that you have never seen this thing before. I'm waiting. You raise up the hand, I unmute you, you talk. Oh, you can as well put in the chat. Yes. Bosco says, pressure gauge something. Okay, Bosco is fine. I'm guessing that is Wesonga. I'm guessing it's a manometer. Wesonga, you're very good at betting. It's very correct. Op says a manometer. Very good. So this thing in senior 2, we saw it and we are calling it to be a manometer. Now, that means that if we are to use this, then we are using a manometer as a thermometer. Very interesting. Now, how does it work? I'm going to tell you, yeah, it's a manometer. Bosco says, yeah, it's a manometer. Yeah, Bosco, the good thing you have remembered. Yeah, it's a manometer. Now, how does this one work? A manometer is used to measure the pressure of the gas. This is the gas. Wesonga, I see your hands up. Please go on, Wesonga. Wesonga.
Yes, teacher. Okay, I have an inquiry. It may not be particularly about this.
Sorry?
I have an inquiry about something.
Yes.
But then it may not be particularly about this exact topic.
It's okay?
Yes. It's something to do with the experiment for saturated vapor pressure where there is a reservoir. Does that
something? Sorry, wait. You're saying something to deal with it?
The saturated vapor pressure.
Yes, experiment to determine the saturated vapor pressure. Yes.
Yes, there is a reservoir, right?
Yeah, there's a reservoir, air reservoir.
Exactly. Yes.
Yes, there's air reservoir in an experiment to determine, to verify variation of saturated vapor pressure with the temperature.
Yes. So does it work in the same way with this thermometer? I'm just asking.
Oh, does it work the same way as this? Oh, good. Now the use of the air reservoir. The use of the air reservoir is to take up the excess the excess pressure, which is going to be created by mercury in that level. Only that I don't have the diagram in a soft copy here. I would have displayed to you. Then you will see what it is exactly. But when you see the use of the air reservoir is between the condenser and the mercury manometer. Do you see? I don't know whether you can recall that.
Yes, yes.
The air reservoir is placed between the manometer, which is the mercury manometer, and the condenser. So this air reservoir is adjustable. It is adjustable so that the pressure can be the same. And why adjusting it? By adjusting, we are saying it is taking up the excess the excess pressure. Oh, it's okay. I think we shall see that in the later time because we have gone too far. But it's okay.
It's okay.
Is that okay, my friend?
Yes, it's fine.
Good, thank you. Okay, so the pressure of the gas here, how does it work? Manometer, this is manometer. It works this way. When you put the gas molecules here, the gas molecules will, of course, exert pressure on this limb. So it pushes this one down, When you push this one down, it raises this one up. So as this one is pushed down, it raises this one up. This one will stop moving at the point when the pressure this side is equal to the pressure this side. And in all cases, here is left open to the atmospheric pressure. So for us to get the pressure of the gas here, to get the pressure of the gas here, the pressure of the gas will be the same as the excess pressure here. This is the extra height, the height on this limb above this of Machor's thread. So it will be the atmospheric pressure, which is on this side, plus the excess pressure, that is plus H. So this is how a manometer works. It helps us to get the pressure of the gas. Now, how do we use it as a thermometer? What we do, we put the bulb. We put this bulb, okay? We put the bulb in steam. When you put the bulb in steam, the gas molecules will expand and the pressure increases. When the pressure increases, we adjust so that it comes back to this level. We adjust this tube. This tube is flexible, it can be adjusted so that the level of mercury, of course, it will go down when you put in the water, when you put in steam. This level will go down. When it goes down, you adjust this manometer so that it comes back to normal. Then from there, you measure this height. When you measure this height, the pressure of the gas, which is at 100 now, the pressure of the gas, which is at 100, will be the same as the atmospheric pressure, then plus the height, which you have just got. Then, after doing that, you put this bulb again in ice. When you put the ice again in ice, we expect the pressure to reduce. So when the pressure reduces, the height of this one raises up. Once it raises up, you adjust this tube to bring it back to the normal. Then you again measure the height, what? The height H. Then the pressure of the gas at that point becomes P naught, which is going to be atmospheric pressure, then plus H what? H naught. Then from there, you put this bulb in an enclosure whose temperature is required. You do the same, you measure the H, then you determine the pressure of that as P theta to be equals to H plus what? Plus H theta. Now, we have P100, we have P naught, we have P theta, so we determine theta from the expression theta equals to P theta minus P naught over P100 minus P naught times 100 degrees Celsius. So this will be the pressure. Is that clear, everyone? Let me know. Is that clear? Wesonga, let me hope your hand is not up by mistake. Wesonga? Okay, you've taken it down. Yeah. John says, yeah. They are antagonistic to each other. Good somehow. Yep. Good. Yes, sir. So that's how it works. Good. So you're saying the bulb with the air is immersed in a substance whose temperature is required. So when you immerse it in a substance whose temperature is required, the substance warms up the bulb, and after warming up, the gas, of course, will expand. When the gas expands, it forces mercury level up. Then, by adjusting the tube, we make sure that the level in A is restored, keeping the volume constant. The difference in the mercury level, that is the other small h I was telling you, is determined as h theta. After determining, you also know the atmospheric pressure is already determined. From there, you can get the total pressure, which is P theta, because the bulb was at theta degrees. So P theta is obtained from P theta equals to H plus H. That one you determine it. After determining, you repeat the same experiment, you repeat the same procedures. But this time round, with the bulb at ice point, with the bulb at steam point. Then you calculate theta from the expression theta equals to P theta minus P naught over P 100 minus P theta, minus P naught times 100 degrees Celsius. Good. John is saying that why is it used as a standard? Why is it a standard to calibrate other thermometer? Very good. This is the most accurate thermometer. The most accurate thermometer. Actually, these are the advantages. This is the most accurate thermometer. Very sensitive, that's the advantage. Wide range of temperature. A standard one to calibrate other thermometers. A standard thermometer, it is used to calibrate other thermometers. Why? Because it is very accurate, and since the pressure of fixed mass of a gas at constant volume varies linearly with the temperature. Now, let me explain this one briefly before we stop. We know pressure law. Pressure law says pressure of a fixed mass of a gas at constant volume is directly proportional to its absolute temperature. So whatever the case may be, as long as you keep volume constant, pressure will always be exactly proportional to temperature. So when you see constant volume gas thermometer, we are enclosing the gas in a bulb which is constant, which is at a constant volume, and so on. And so it is only pressure which is varying with the temperature. And the fact that pressure is directly proportional to the absolute temperature, it makes constant volume gas thermometer very accurate. Do you get me? Not only very accurate, but also to be used to calibrate other thermometers. Do you get me? Is that okay, everyone? Please let me know. Is that fine? Oh, yes, I do. That is Isaiah. Good. Yes. Good. Joe Lavin says good. Oh, good. Understood, sir. That is Joan. That's great. Oh, that's great. Yes, sir. Yes, yes. Everybody's saying yes, yes. Good. So that is why it is used to calibrate other thermometers. Very accurate, since in constant volume gas thermometer, the volume is kept constant, and the pressure of a fixed mass of a gas at constant volume varies linearly with the change in temperature. We are going to see only disadvantages. It is bulky, very big. Then 2, it does not give direct readings, so it requires a skilled person. Then it does not measure rapidly changing temperatures. Those are the disadvantages. Then lastly, as we wind up, teacher, I can no longer hear you. Can the rest hear me? Hello, can the rest hear me? Let me know. Yes, yes, yes. People are saying yes. So, John, maybe the problem is your network. So let's see the correction. There are 2 sources of errors here. I want to be very brief here, and then we end the lesson. We have gone already past time. There are 2 problems here. 1, we don't take into consideration the expansion of the bulb. That is the first error. You know, when you put in steam, the bulb is matter. So if it's matter, it's expected to expand. But then why do you say that why do we say that the volume is constant? No. The bulb has to expand, and so the volume has to increase. But because we make an assumption that there is no expansion of the bulb, it makes it very accurate. But in the real sense, the bulb is supposed to expand. And so it brings some errors. That is 1. Then number 2, when I put the bulb in steam, the temperature of the bulb will be at 100 degrees, degrees Celsius. But this one, which is not in steam, there's this part which is not in steam, is not at 100 degrees Celsius. It's not at 100 degrees Celsius. And yet it's going to mix with this. So,
teacher, hello?
Yes, please. I'm just winding up. Let me end.
Okay.
Call it. So the problem comes, this space is called the dead space. This is what we call to be the dead space. So it brings a problem here because you put only the bulb at 100 degrees Celsius. What about this part? And yet it contains the gas molecules. So this one remains at the temperature of the room, and this one remains at the temperature of 100 degrees Celsius. And at last, when these 2 gas molecules mix up, the final temperature is not 100, it's less than 100. That's why we come and say, because its temperature lies between that of the bulb and the room temperature. So those are the sources of errors. I thank you so much for listening. I'm going to put the work in our Google Classroom. Please check very well. Check very well in Google Classroom. I'll send it there, and you copy the work together with the assignment or the exercise. Thank you so much for being part of this. I challenge you, please, to do the everything, exercises and the rest. Thank you so much. Let me call upon my admin to give closing remarks, and he closes the meeting. Yes, Mr. Bernard. Yes, Mr. Bernard.
Yes, Alira.
We are done.
Yes, thank you. Well done. We can end.
Okay, please. Thank you so much. Members, nice lunch.